I can see myself. I can see the, yeah, I can see the software recognizing that I'm talking. Yeah, well, I'm talking now. That's as voice. Yeah, I don't know what's happening. Which room is that? Can you please text me from both rooms? The teaching assistants from both rooms. So B208 doesn't have voice. Does 204 have voice? Can you please do a thumbs up or something? Okay, so it's not my problem. So I will wait for you to fix it. I don't know. There's nothing I can do to fix the sound in the classroom. Okay, I'll wait a couple of minutes for the voice thing to be fixed from class 208. I'm sorry for the delay, but it is not a problem from my side. It's a problem from the classroom itself. I don't know, the sound settings of the classroom. So just be patient. Hmm. Yes, can you hear me now? 208. Can you hear me? I'm now speaking actually, but I see the teaching assistant from 208 being connected, but still no sound. I'm not sure what's the problem. The technical support has been called to 208, so I apologize. I apologize to the materials group because they can actually hear me because we're not starting, but it's a technical problem. So I'll turn off. I'll stop the video from my side and wait a bit until maybe the technical team fixes the problem. Hello, 208. Can you hear me now? Okay, good. So, apologies for the delay. Nothing from my side. I think it was a problem just from the settings in the classroom. Anyway, let's get started. A minor delay. So I was saying we started talking on Monday and Tuesday, on Monday actually, about thermal transitions in polymers, and we said that there are three main thermal transitions in polymers: is the glass transition, the melting point, and the crystallization temperature. Okay, we started talking about we talked about the glass transition. Actually, we said it is the point where we provide enough thermal energy to the chains in order to change their conformations, okay, and for a material from its glassy state to pass onto a soft state, an elastomeric kind of state, okay. And now today and next Monday, we will be talking about the crystallization and melting temperatures, which are also two very important temperatures that dictate how do we fabricate the crystalline structure within polymers and how we destroy the crystalline structure within polymers, okay? Fabrication or growth of crystallites is taking place via crystallization. And of course, as we can realize, destroying those crystalline sites takes place during the melting process, okay? So we will talk about phase transitions, we will talk about what are the conditions for the crystallization and the crystallization process itself, how do we define a melting point, and how do we essentially grow crystals, okay? And what is the technique in order to evaluate these things. And let's go, sorry, let's go a step back again and discuss again a bit about the structure of polymers, because it is very, very important. The structure of polymers is very important because all thermomechanical properties of a polymer are given to a specific structural state, okay? 100% amorphous polymer behaves completely different in relation to a semi-crystalline polymer or a fully crystalline polymer, okay? So there are three main physical states that are characterized by specific morphologies. A fully crystalline state, which corresponds to a perfect ordering of the macromolecular entities, okay? So for a fully crystalline material, we have perfect packing, and the chains look like that, okay? It is very, very difficult to fabricate a fully crystalline material. You need to follow very, very specific polymerization procedures, and also you need to be to follow very slow processes in order not to induce any impurities or not to induce any, let's say, entanglements with the chains, okay? So it is a very, very slow process, and 100% crystalline polymers only are used for research purposes, and they're not absolutely produced by any industry or so. So besides the fully crystalline phase, we have the amorphous state, okay? We talked about that. It is a disordered entanglement of polymer chains, okay? So it is disordered. Okay, so it's completely random, it's completely disordered, and it has completely different characteristics compared to a fully crystalline material. And a combination of the two, which is the most important, most interesting, let's say, in terms of behavior, is the semi-crystalline state, which comprises of both amorphous and crystalline state in varying proportions, okay? And the varying proportions lead to different degrees of crystallinity. Most of the times, semi-crystalline material, this is a semi-crystalline, these materials have a degree of crystallinity, that is the degree the degrees of crystallinity usually in semi-crystalline polymers that are also produced by industry is commonly in the order between 20 and 80%, okay? So if it's 20% of the polymer is crystalline, so it shows this type of crystals which are ordered, okay? These are the crystalline regions. And if it's, as I said, 20% crystallinity, then we have 80% amorphous chains that are completely entangled. Okay? We said each of these states, the crystalline, the amorphous, and the semi-crystalline, exhibit specific thermomechanical properties and responses, with the semi-crystalline state having combining properties of both amorphous and crystalline states at a macroscopic level. Okay? So the transition from a rubbery state to a viscous liquid state that sets the minimum temperature that the polymeric materials can be processed, and that is the transition from that's the melting point, okay? And we said that the transition from amorphous materials from a glassy to a liquid state, it is the glass transition temperature. Okay, and it from the beginning of let's say of polymer science, from the inception of the polymer science, it has been recognized that polymer molecules have the ability to crystallize. Okay, and the main characteristics of polymers is that that distinguishes them from other crystalline solids is that they can have a semi-crystalline form. Okay. Normally, polymers are semi-crystalline. Okay. Now, if we want to consider of how do polymers crystallize, okay, is to imagine polymers, the molten state of polymers, as a big ball of tangled, let's say, spaghetti or noodles. Okay. So in this case, we will have a molten state. The chains are completely randomly allocated within the structure. Okay. But if we freeze this down, okay, and if we want to consider a semi-crystalline material, it's like this pack of noodles that has not been boiled, and you can see that there are regions that are ordered. Okay, the majority of noodles might be in completely random state, but you can see that there are states like here, let's say, or here, or here, let's say. So here we can have a semi-crystalline approximation. Okay. The actual strands of polymer spaghetti will have a length to diameter ratio of 1 to 100. Okay. So for the polymer's diameter to length ratio is 1 to 10,000. So you can realize that it is very remarkable that such a random mass could crystallize and give an ordered structure and clearly significant molecular rearrangement and considerable cooperative movement is required for crystallization to occur. Okay, that is if we freeze this. Of course, in reality, this is not the case, because it's a bit difficult to obtain from a molten for a cooked pack of noodles to obtain this state. but we're trying to approximate this in polymer science, okay? And we talked about the different transitions in Tuesday and in Monday, and we said about amorphous materials. We said that they only have a glass transition, as a result of their random molecular structure. And we also said something that is important, that the glass transition is a second order transition. And why is that? We said glass transition is a pseudo actually second order transition because it depends on the heating or cooling rates. Okay, so the value that we get of the glass transition, that is the glass to rubber transition, depends on the heating and cooling rates we apply experimentally. Pseudo depends on heating or cooling. Remember that the glass transition, in the glass transition, we don't have an abrupt increase, a significant increase of volume, of enthalpy or entropy at the glass state, but we just have a change of slope here, okay? On the contrary, for crystalline materials, which have, we said, have ordered molecular structure, you can see that here we have a abrupt, a significant increase in volume, okay? I forgot to upload my notes on the glass transition and the structure on QM Plus. I will do it today, so you also have these notes. What I'm writing on the slides, you have my notes as well. So here for the melting point, we have an abrupt increase in volume, but not only in volume. We said that we have a significant increase in enthalpy or entropy as well, okay? And that is why we consider the melting point as a first order transition. So for semi-crystalline materials, we said that from a semi-crystalline state, if we heat the semi-crystalline material, of course, that is the arranged chains, okay? You can realize that we have many more chains surrounding the crystalline states. So for a semi-crystalline solid, if we heat it, we destroy any crystallinity, okay? So by heating, we have destruction of ordered, that is the crystalline regions. Okay? And also in the melt state, in the liquid state, if we cool it down slow at normal ranges, not very, very fast, this is amorphous, okay? So from the amorphous state, from the melt state, if we cool it down, we can induce nucleation and growth of crystallites, and then we can again obtain these ordered regions and a solid semi-crystalline material, okay? So it is important to point out that the factors that we discussed the other days, regarding what affects actually the temperature of the glass transition are very similar to the factors that affect the melting point, okay? And as I write here, both the glass transition and the melting point increase with increasing chain stiffness. So the stiffer the main chain that we have, the more thermal energy we need in order to pass, either for a semi-crystalline solid, let's say, to pass from the glassy state through the glass transition and then through the melting point. And we saw the graph of the modulus versus temperature, where we have here the glass transition and here we have the melting point. So we need continuous increase of thermal energy, okay? So initially, we need the increase of the thermal energy in order to have the chain start moving, okay? And change their conformations. In that case, we pass through the glass transition, and then we start disentangling our chains. So we have chain slippage, and once we have chain slippage, the chains are able to freely move within the polymer, the molten polymer. So we have passed through the melting point, okay? And that demands providing specific amounts of energy. As you can realize, to change a conformation of a polymer, it demands less energy compared to a complete disentanglement of the chains, okay? Complete disentanglement needs very, very significant movement from the side of the chain. So yeah, we said melting point and glass transition are affected by increasing chain stiffness. And we discussed that chain stiffness increases by bulky side groups, polar groups or side groups, and double bonds or aromatic chain groups such as benzene ring and so on. It is very important, though, to point out that the regularity of repeat unit arrangements affects only the melting point. And the regularity of repeat unit arrangements, does anyone remember what is the regularity of repeat unit arrangements? We discussed it on the structure in one of the first classes that we did. How is it called in polymers? The regularity of repeat unit arrangements. Can anyone text me? How is it called? The way that we arrange repeat units, that is either side groups or functional groups or something else in a polymeric chain, affects the melting point. Do you remember how we call the regularity of repeat units? That is called, I don't see any answers, that's fine, don't worry. That is called tacticity. Yes, very well, John. Said tactility, but it's fine. It comes from the Greek word tactikos. And it essentially tells us how regular do we have the repeat unit arrangements. So we have three types of tacticity. We have isotactic, which are all in the functional groups are all regular in one side of the main chain. We have syndiotactic, we have functional groups or side groups in alternating sides of the chain, but in regular arrangements. And then we have amorphous, a random tacticity, which is the repeat unit arrangements is completely random. Okay, we will see a bit more regarding that later today. So something else I want you to notice is that the glassy state, the volume of the glassy state is higher than the volume of the semi-crystalline solid, is higher than the volume of the crystalline solid. And of course, that has to do because the packing of the chains is completely different, okay? So you realize that in the glassy state we have like an amorphous bulk, and then in the semi-crystalline solid you have both the amorphous but also some crystalline regions. So the crystalline regions reduce the volume because we have ordered structure, and obviously for the crystalline solid we have the maximum order in that we can achieve in polymers, and in this case we have the minimum volume that the chains can uptake. Okay. So in terms of the melting point, let's start with the melting point, and let's start discussing essentially what is the melting point. A melting point essentially is the reverse or inverse, let's say, inverse of crystallization. We said that in the melting point we destroy any crystalline arrangements, and in crystallization we fabricate, we create those crystalline arrangements, these crystalline regions within the polymer. Okay. It is important that in the melting point, the free energy, the Gibbs free energy is constant. Okay, so the solid and liquids are in thermodynamic equilibrium. Okay, so the solid and the liquid are in the same state, relaxing state, and there is essentially no problem between the two of them. So that tells us that the Gibbs free energy is equal, but the Gibbs free energy is given by this very simple equation. The Gibbs free energy equals to the enthalpy minus the temperature times the entropy. Okay? So if we take this very simple relationship, we end up with this equation that the melting point equals to the ratio of the enthalpy over the entropy. Okay? And let's have a look at what is each each unit here. The enthalpy difference between the crystals is obtained by between the crystal and liquid is essentially the heat of fusion. Okay, and it is determined by the interaction forces. So the stronger the interaction forces, the higher the heat of fusion is within polymers. Okay, but the most important thing here, I guess, is the entropy. Okay, and in simple terms, I want you to remember that the entropy shows the degree of randomness within a polymer structure. Okay, so the more amorphous is a material, the higher degree of randomness that we have. Okay, and it's obvious if you check the entropy of a crystal conformation, and if you check the entropy of a liquid conformation, because in the liquid state the chains are able to freely move compared to the crystalline conformation where we have this ordered structure, obviously you realize that the entropy of the liquid is much higher than the entropy of the crystal. Okay? So it is related to the degree of disorder within the different situations, different states in a polymer. And also it can be resulting from probabilities of chain conditions in both phases. But you realize that the probabilities to have different forms, different conformations, different chain conditions in liquid is much, much higher compared to the probability of having different conformations in crystalline chains, okay? So yes, that's what I was saying. So the entropy is controlled by the increase in the number of conformations upon melting, okay? And we said that the melting point equals to the ratio of enthalpy over entropy. So the enthalpy is mainly affected by interaction forces. And I have some very simple examples here, such as, let's say, look at the difference between polypropylene and polyvinyl chloride, okay? You can see that this difference is around 90 degrees Celsius. Why is that? It's because the polyvinyl chloride has a side group of chlorine, while the side group of polymer is a methyl group, okay? So PVC, sorry, give me a second. Table, right? So the PVC consists of molar molecules which are attracted to each other by dipole-dipole interactions, okay? That is due to electrostatic attractions of the chlorine atom. And because the chlorine atom can induce these electrostatic attractions, it has more significant interaction forces. And because the interaction forces are more significant, delta H of the PVC is higher than the delta H of the PP. And in this case, the melting point, Tm of PVC, is higher than Tm of PP. Okay? And also we said that the change stiffness is what affects significantly the entropy of the system. And you can realize that polyethylene, which has the simplest form of a macromolecular chain, yeah, the polyethylene, which has the simplest form of macromolecular chain, is much lower in terms of the polystyrene, isotactic polystyrene, because you remember that in isotactic polystyrene we have a bulky benzene ring as a side group, okay? We have a okay, and because we have this benzene ring as a side group, the movement of the chain becomes much more difficult, and because of that, the chain stiffness becomes the delta S becomes much lower. Okay, so in this case we have delta S of polyethylene is higher than delta S of PS because the conformations that the polystyrene chain can take are much smaller than the conformation of a polyethylene chain. And because of that, Tm of Pe is higher Tm of Ps. Okay? It is very simple. There is also a slight influence by the chain length, which is given by this simple empirical equation, where A and B are constants for each polymer. And you can realize that if you need to use this equation A and B need to be given to you. You shouldn't know or remember or anything else. I'm saying here that there is a slight influence by chain length, okay? And here I have a molecular weight value. What type of molecular weight is affected by the chain length? If you tell me that and we take a 10-minute break. Anyone in the chat? Which type of molecular weight is affected by chain length? Anyone? We said that different types of molecular weights are affected by different types. So if this case will have an influence by chain length, what type of molecular weight should we use in order to observe this? No answers. I don't want to take time of your break. So in this case, we'll have the Z average molar mass, okay? Because the Z average molar mass is the one that is affected by the length of the chains more significantly, okay? So 10-minute break, and we get back to continue discussing about what are the factors that affect the melting point. Okay, grab a seat so we can get started. So we said earlier that the factors that affect and the glass transition that we discussed the other day are very similar to, or identical, let's say, to the factors that affect indeed the melting point. And why is that? It's because approaching the melting point, essentially what it needs more, even more thermal energy than the glass transition. I just saw some of your messages on Wacom. I'll answer them once we finish the class. Okay. The one that I see the easiest one. Why the M refers to MZ. By M we essentially mean the molar mass of the polymer. Okay, and here we said that there is a slight influence of the chain polymer by evaluating the chain length. When we have a molar mass that is mostly related to the chain length is the Z average molar mass, because the Z average molar mass is the most sensitive type of molar mass averages that evaluates the chain lengths. Okay, we said that we have three different types of molar mass averages. The number average molar mass, that it depends on the number of chains. Okay, the weight average molar mass, that depends on the weight of the chains, and the Z average molar mass, that depends on the chain length. Okay, because here we have a slight influence of the chain length onto the melting point, we can say that the Z average molar mass is the more appropriate, let's say, average molar mass that we need to evaluate for approximating, let's say, using this empirical equation to calculate the melting point. Okay. Yes, and I was saying that the melting point has very similar characteristics to the glass transition in terms of the factors that affect the melting point. Simply because we said that we need thermal energy in order to induce movement in the chains, initially start changing the conformation of the chains through the glass transition, and then by providing even more thermal energy, we induce a rotation around the bonds, okay, around the chemical bonds along the chain. Okay, so obviously when we have strong chain bonds, we have higher glass transition and higher melting point. Okay, because we need more energy in order to break these bonds. On the other hand, when we have introduction of weak bonds, of weak groups such as carbonyl groups, or just oxygen groups in the main chain, that adds to flexibility. And because it adds to flexibility, then we can have a relative decrease. So from the polyethylene repeat unit here, you see that if we add just one oxygen group, we reduce more than half, almost half the melting point. While if we have a carbonyl group, we can reduce it a bit, or not too much as the oxygen group, because the carbon-oxygen bond is much stronger than a simple oxygen bond. But still, it is reduced significantly compared to the melting point of polyethylene. Okay, that is the simplest polyethylene, not low density or linear low density or anything else. Okay. On the other hand, we said if we have presence of bulky groups such as phenyl rings or benzene rings or whatever, that increases the chain stiffness and causes a large increase in the melting point. Also, for the amide linkage groups, it allows intermolecular hydrogen bonding to take place, okay? And we said that when we have stronger intermolecular bonds, okay, that makes the interactions between chains more strong, okay? And because the interactions between chains are more strong, then again, we need more thermal energy, okay? So that leads to a raise of the melting point because we have hydrogen bonding between chains. We said that the weakest type of intermolecular bonding is van der Waals bonds, but hydrogen bonds have significantly more strength, and they need more energy in order to break these bonds. So when we have intermolecular hydrogen bonds, that means we need higher thermal energy to destroy these bonds. Okay. And finally, side groups. Side groups is a bit of the situation with side groups can be a bit unclear. The thing is that we saw already that the presence of long side groups, okay, can add to the fabrication of free volume. Okay, so we have a main chain. If we have some side groups like that, it adds to creation of more free volume. But it's not that simple, because sometimes we may have, if we have bulky side groups, then we have a raised chain, or the melting point, okay? And also, if we have extremely long side groups, as one of your classmates pointed out to me, and I must say that I wasn't aware of that long side groups. If you have very, very long side groups, in this case, you create more entanglements, okay? And because you create more entanglements, you slightly increase both the glass transition and the melting point. So the situation with side groups can be a bit unclear. So every time you need to very clearly identify what is the length in order to understand the effect of the side groups onto the thermal transitions, that is the melting point and the glass transition. For normal side groups, in the order of, I don't know, 4 or 5 side groups attached in a sequence, such as what we saw with polymethyl methacrylate, which became polypropylene, polyethylene, and so on. For up to 5, let's say, side groups, that leads to a creation of more free volume, and any type of entanglements may be not too significant compared to the creation of free volume regarding the increase or decrease, in this case, of the melting point of the glass transition. But as I say, the side groups is the presence of side groups can be significant. We need to every time identify the case of side groups. That is, if the side groups have bulky or a very large, let's say in terms of mass, side groups, these increase the stiffness and increase the melting point at the glass transition. If they are relatively small in terms of length, that leads to a creation of more free volume. And of course, if they don't have any bulky groups there, that leads to creation of free volume. And in this case, we have a reduction of melting point and the glass transition. So we take each case very differently, okay? So you can see here, just by adding 2 methyl groups or 3 methyl groups here, we reduced around 100 Celsius degrees difference at the melting point. But once we have more complex side groups, or such as phenyl rings over there, that leads to an increase of the melting point of around, I don't know, 60, let's say. 60 Celsius degrees, okay? As you can realize, because we were talking about the the melting temperature, and we said that the melting temperature depends on the ratio of the enthalpy over the entropy, okay? So you realize that the chain orientation plays a very significant role onto the entropy values. So what happens when we stretch a polymer, okay? When we stretch a polymer, essentially, we align the chains along the direction of stretching, okay? From if we have an amorphous mass of polymers like that, of chains like that, if we stretch it along this direction, we start to align the chains, okay? And by aligning the chains, what do? We reduce the entropic degrees of freedom, okay? So stretching leads to a reduction of the entropic degrees of freedom. What are the entropic degrees of freedom? There are the number of statistical states that are available to polymer chains, okay? So the less, let me write it down, number of statistical states available polymer chains. So when we stretch, we reduce the entropic degrees of freedom. And what does that say? It tells us that the chains do not have many options in order to take different forms. Okay, if you make a chain random, you have like a million different types of combinations you can do. If you make them straight, there aren't too many types of conformation that these chains can take. Okay, so you can realize that with stretching, we reduce the entropy. And by reducing the entropy, that leads to an increase in the melting point. Okay? It is very simple. That is very important in the case of elastomers, as we will see, which are amorphous materials, fully amorphous materials. And because we're stretching and we're orienting these materials, we create crystallites in there. And so in this case, we create kind of a composite, let's say, which is a semi-crystalline material, even though we were starting from an elastomer. And you will see that it displays unique stress-strain curves, which are not what is expected from the theory, okay? And that is very interesting and important. We will see that in the relevant part of this course in elastomeric materials, okay? And let's see some. Let's have a look at some characteristic melting points of polymers. Some of these are good to remember. These you should know what is approximately the melting point of polyethylene, which is around 135. Polypropylene around the 65, 170. The melting points are very important. As you can realize, because if we want to process a material and fabricate something, we need to know its melting temperature. So we first melt it and we process it more easily at the melt state in order to bring it to the form that we want, okay? So they're extremely important. For polymer processing, okay? We will discuss a lot about different types of polymer processing also later this semester, and let's say which thermal transitions we use every time for different types of polymers, okay? You can see that for polyethylene oxide, just the introduction of an oxygen group reduced significantly the melting point, okay? Here, just the introduction of a small side group made the polymer indeed added a bit more volume, but the truth is that in this case, if we have an increase of the melting point, because the chain is already very flexible, okay? So in this case, even though we added more volume, the side group, the methyl side group led to an increase of the melting point, okay? That's why I'm saying that it's not very straightforward every time what the effect of the side chain will be, okay? It depends on the situation based on each polymer, okay? So there is no, don't take it like a rule that exists every time for the effect of side groups onto the melting or the glass transition. You can see all these materials with bulky benzene rings, how high melting points do they have, and essentially look how high is polypropylene, which has a very short chain, and the main part of the chain is a benzene ring. So because of that, it is very, very stiff, okay? And because it's very stiff, we need a huge amount of energy in order to break these materials down and melt them, okay? And a bit of sum up, we said that the melting point can decrease because we have disturbances in chain regularity, okay? When we have branching, it can lead to a more free volume. We have a melting point decrease because of the effect of the crystallization temperature. But what I mean here is that when we have low crystallization temperature, we have small imperfect crystals, okay? When the crystals are not perfect, they are small, it's easier for us to melt them, okay? So you can realize that when you have a crystalline region that is that big, okay, within an amorphous material, and you have a crystalline region that is that big, as you can realize, there is higher perfection here, and larger crystals. So when we have larger crystals, we need more energy to break them. That's very straightforward to understand, okay? So when we do a fast crystallization, we will see what fast crystallization means. Fast crystallization means pretty much cooling from the melt at high cooling rates, okay? We can either use fast cooling rates or slow cooling rates. When we get slow cooling rates, we allow enough time for, sorry, I think my camera was stuck. So when we have fast cooling rates, we don't allow enough time for our polymer to relax, and that leads to lower crystallization temperature. When we have slow cooling rates, we allow enough time to the polymer to relax, to grow the crystalline regions more perfectly, and in this case, we have more perfect crystals, larger crystals, which indeed need more thermal energy to break. That leads to a higher melting point, okay? So we have small crystals, and we also have imperfect crystals. And both of these lead to lower Tm, okay? That's what I'll say here. Crystal imperfections leading to melting temperature range. Yes, I should point out that we say that crystal imperfections leading to a melting temperature range. If we have imperfect crystals, we have a broader temperature range. And what does that mean? We mean that when we evaluate the melting point, the curve can look like that. That is the enthalpy over temperature, and what I will explain this about the direction of endotherm and so on. So in this case, when we have imperfect crystals, it can look like that. Well, if you have more perfect crystals, it can look like that. You can realize, or maybe let me correct it a bit. Oh no. Right. Anyway, I'll fix it. So we have here and okay. Generally, the melting point will be the same, but you can see that we will have a more narrow range of temperatures. As we said for the glass transition, the melting point is not just a single value of melting point. Even though we take single values, you can see that there is a temperature range. Okay, you can see that here we have a temperature range, and when we have more perfect crystals, the temperature range is more narrow. Okay. And also, as you can realize, the imperfect crystals, the small crystals, gives low melting point, as we said. You see here and here, small crystals are much easier to break because they don't need that much energy. Now, there is an empirical relationship between the glass transition and the melting point in order to calculate one of the two if you know the other. But I should point out that this is empirical, okay? It should not be used as, let's say, an absolute method in order to calculate the glass transition or the melting point if you know one or the other, okay? And the reason why this relationship essentially exists is because we said that there are a lot of similarities in the factors that affect the melting point and the glass transition for polymers, okay? So there is these empirical relationships here that the glass transition is the half of for the melting point for symmetric chains, okay? So what are symmetric chains? Symmetric macromolecular chains is when we have short repeating units consisting of up to 2 main chain atoms, okay? In this case, can be polyethylene, polytetrafluoroethylene, so, no, sorry, PTFE, polytetrafluoroethylene, I guess, yes. So PTFE is like that, okay? You remember that. So this is a symmetric chain. While for a polymer with asymmetric chains, we have this relationship that the glass transition is the 2/3 of the melting point, but very, 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 very important. These calculations should only take place in Kelvin, okay? If you're going to do these calculations, such as this example here, a polymer with asymmetric chains that has a melting point of 250, then we have we transform the 250 Celsius degrees onto Kelvin units, and after this transformation, 250 times 2/3, yes. So we transform this to Kelvin, and then we multiply by 2/3 in order to find the glass transition. Okay. I repeat, this is an empirical relationship. This shouldn't be treated, let's say, as as a relationship that is always very, very accurate, but it can give us some indication about the range of temperatures that we can observe the glass transition. Okay. And before summing up for melting, again, I should point out that it is not possible to define a single melting temperature. As we said, for the glass transition as well, we said that, we said that the glass transition can look like that, okay? And this region here is approximately the glass transition region. The same applies for the melting point. Here we have the heat flow, the temperature, direction of endotherm is down. What did I put before? Endo up, endo down. So in this case, we can see that we have a range of values here that can be taken also as the melting point, okay? And generally, this region here is considered as the melting region, okay? So we have a range of values that can be approximated within the region of melting, okay? The units are watt per gram. And of course, both of these depend on the specimen history. That means how fast or how slow they have been cooled, and the temperature of crystallization. Okay, that of course, that, as we said before, that is related to crystalline perfection or size. Okay, and obviously, as we explained for the glass transition temperature, the melting behavior also depends upon the rate of heating of our sample. Okay, so that is essentially given by differential calorimetry. Okay, this is a very standard equipment in calorimetric equipment in performing studies of the thermal transitions in polymers. It is the most common polymer, let's say, evaluation instrument for transition temperature. And also remember that for fast heating, that leads to higher melting points. Because we said, similar to the glass transition, we do not allow enough time to our polymer to relax, okay, in order to take the different conformations. So we heat it fast, and there is not enough time for the instrument to analyze precisely what is happening. So fast heating leads to higher melting point and a higher range of melting temperature, okay? Okay, so you can realize that there is some variability in the melting behavior, and that is why a final concept that we will be discussing in terms of melting, named the equilibrium melting temperature, has been introduced, representing the melting of an infinitely large crystal that is essentially a polymer. That is a polymer that is 100% crystalline. Okay, so if we know that we can fabricate 100% crystalline polypropylene, in this case, once we know the equilibrium melting point of it, we should not observe any variations above this temperature. That is the maximum temperature of melting that we can observe for a polymer that is 100% crystalline. Okay, so there is not a method in order to calculate the equilibrium melting temperature very accurately. Okay, so what we do is heat and cool our polymer at the same heating and cooling rates, and obtaining the melting point and the crystallization temperature. So a specific melting point at a specific crystallization temperature at a specific cooling or heating rate. That is the same. That is the same heating cooling rate. So we use the same heating and cooling rate in order to obtain this melting point over crystallization values. Okay, and then we fabricate these experimental values. We take these experimental values for different heating and cooling rates, and we create this linear fit here. Okay, and we extrapolate this linear fit here with this equation here. Let me use a different color. We extrapolate this red line to find the blue line, which is the blue line equals to melting point equal to crystallization temperature, and we obtain that is the equilibrium melting temperature. Okay, I repeat, that is a single temperature, not a melting region, not a temperature region. That is a single melting temperature and not temp region, at which all crystals have been destroyed. Okay, we cannot find a I repeat that we cannot find a melting temperature for a specific polymer that can be higher than its equilibrium melting temperature, and that is because the equilibrium melting temperature refers to 100% crystalline polymer. Let me write this down and we move on. Refers to 100% crystalline polymer. Okay. Again, I repeat that this process that we discussed with this graph, it is an estimation. Okay. That is why the equilibrium melting temperature is not a very commonly used concept. Okay, we simply take the values of a DSC or some other value that we get in order to process our polymers. And now let's go through an introduction of the crystallization process. Okay, we said we started from the simplest thing, and the simplest thing is in life essentially and in nature is to destroy something. The most difficult thing, however, is to create something, and not only create something, but create something as perfect as ordered crystals from chains that are extremely long. Okay, so you can realize that the crystallization process is truly unique, because from from a crystalline, from an amorphous state, from a liquid state where we have complete movement of huge chains. You realize how huge these chains are, okay? How many carbon atoms? We're talking about tens of thousands carbon atoms within the main chain, okay? And from a liquid state where we have complete random movement and slippage between the chains, we end up obtaining crystalline regions, okay? So crystallization is generally the process where an ordered structure is created, is produced by a disordered phase. Usually it is from the melt state, or sometimes we have a solution crystallization, but here we will be mainly talking about melt crystallization. To simply explain to you what is solution crystallization is when we use a solvent to dissolve a polymer, we have a mixture, a liquid mixture of a polymer and a solvent, okay? Then if we slowly evaporate the solvent, we will still create a solid polymer, okay? However, this process also needs to be we need to control very accurately the evaporation of the solvent in order to create crystalline regions, okay? If we induce evaporation of the solvent very fast, then we will have very few crystalline regions because, again, the chains won't have enough time to order themselves. And the same applies when we cool down a melt in order to create these this crystalline region, okay? So when the temperature of a polymer melt is reduced to the melting temperature, then there is a tendency of the entangled molecules to become aligned, okay? And form these ordered regions. So the formation of these ordered regions starts happening around the melting temperature when we cool down from the melt, okay? We have the melt, we cool down, and when we're passing through the melting temperature, the molecules start to become aligned, okay? This process is called nucleation, okay? And the ordered regions are very small in this case, and these are called nuclei, okay? Closer to the melting point, we have aligned small regions, which are called nuclei, which are stable only below the melting point, okay? Because above the melting point, they are disrupted by thermal motion, okay? Let me write this down. Above Tm, they are disrupted by thermal motion, okay? So the second step in the crystallization process is then the growth, okay? Where in this case, growth takes place by addition of further chains, okay? So we start having creation of these small regions, and then we have addition of more chains, so we have a growth of the crystallites, okay? So a crystallization is a two-step process, okay? A process that takes place by initial nucleation and then growth, which may be considered separately, okay? And let's have a look at this graph, okay, essentially, where we have the Gibbs free energy for a liquid and a crystal, okay? And I should point out that the system essentially always wants minimum Gibbs free energy in order to be stable, okay? System as this is more thermodynamically stable. Okay, so as you can realize, below the melting point, we have the minimum state being the crystalline state. So here we have a, let me use a different color. Here we have a stable solid. Okay, but above the melting temperature, we have the liquid state that is more energetically stable. Okay, so in this case, we have a stable liquid. Okay, the actual crystallization, as we said, it is affected, and this is the delta G every time. Okay, we said that for temperatures lower than the melting temperature, the enthalpy of the crystal is lower than the liquid, and that is energetically favored, more thermodynamically stable, and that is why crystallization takes place. So if you move towards this direction, that is why we have formation of crystallites. That is cooling, okay? What time is it? 38, okay. Yes, we have, as we said earlier, the fact that crystallization is affected by two separate processes. Okay, we have the nucleation, which is the most important part of the process, because nucleation essentially is the part where we initiate crystallization. It is the first step in order to start crystallization, and that is order that is stimulated by intermolecular forces. So the forces, van der Waals forces between chains, act and they compact the chains. And it is taking place because of thermal or density fluctuation. That is by controlling the cooling rate or controlling the density of our system. I'm pretty sure you've seen this experiment where you put a bottle of water in the freezer, okay, and you see that when you take it out, it's still liquid, but when you cool it down very fast, that causes a density fluctuation, and then it crystallizes immediately. Okay, that is what is a density fluctuation. And also, in order to induce induce nucleation, we use some particles or sometimes some impurities that are present within our polymer, where nucleation takes place at these sites. Okay, by particles. This can be I don't know, additives such as fillers or pigments, pigments, and so on. Impurities can be, I don't know, dust, maybe. Dust that is present within a reaction vessel and so on. And the second part of crystallization is the growth, where essentially after we have the nuclei, okay, the nuclei attract chains, and we have recruitment of chains to the nucleus, and we have the formation of these, let's say, ordered regions within the polymer. Okay, we will stop here. I don't want to take more of your time. I know that you have a class. I don't know, is it Colin or someone else? So it was good seeing you this week. We will continue next Monday with the crystallization process, and we will also do a quick multiple choice questions in order to revise what we said about the thermal transitions. Enjoy your weekend and see you on Monday. Bye. I will answer your questions on Wacom now. Okay.